it's going to be explaining things like this picture, right? What's this picture of?
Carmen Street.
Sorry, yeah, Von Karman Street, right? Vortex Street. This is flow past a cylinder that for sufficiently high Reynolds number undergoes this inspection, and that will be completely explained, we'll say, in this class using these techniques. And here is another thing, movie I wanted to show you. Where is this movie here? Here is the Faraday waves. This is what happens when you oscillate a fluid layer from below. So what we're talking about is not merely notation and little tiny matrices. I'd like to think it's, we're actually, I mean, I'm not going to stop at just showing you this movie. I'm going to talk about the equations and how you reduce equations to what we're talking about. So have faith that it will go from little tiny algebra to something a little more real. Okay. So it's here. Okay, so now, okay, so one last little detail about these. We had just done this Jordan normal form thing, and you remember when you learned how to solve constant coefficient differential equations, you learned that you had to write solutions. You know, if you have a, if you have C1 x double dot plus C2 C1 x dot plus C naught x equals 0, you know that you're supposed to write x equals e to the lambda t, right? And then you get C2 lambda squared plus C1 lambda plus C0 equals 0, and you solve this and you get your lambda, right? Okay, and so you get your two solutions, so you have e to the lambda 1t and e to the lambda 2t, right? Everybody remembers this. But of course there are circumstances under which you get only one root, right? And what are you supposed to do? The two solutions are then e to the lambda t and t e to the lambda t. Everybody remembers that? So this is indeed the case with, since our whole purpose in studying...
It's on the floor.
Oh, thank you. Thank you. Yes. The whole purpose in studying these eigenvalues is to get evolution equations. Indeed, that's what happens. That is to say, if you have a system, if you're studying a linear system whose Jacobian, excuse me, if it's a linear system, then it's going to be governed by a matrix. It's x dot equals matrix times x. And its solutions are of that kind. That is to say, there's an exponential, and then there's also an exponential times t. And if you look at what happens in the evolution of an initial condition, it will undergo, even if the lambda is negative, so you say, oh, it's stable, it's going to die off exponentially, yes, but initially it will grow. And this gives rise to a phenomenon called transient growth, which was extremely fashionable in the middle 90s. It's having to do with transition to turbulence, but it's fallen out of fashion now. But I tell you this to illustrate what I'm going to, it was, right? When you say very fashionable, but no longer talk about it. There are fashions in science too. You don't think about it. Afterwards, you're only, it's like movies, right? The old movies, oh, they were so good. That's because only the good ones survive, right? You don't talk about the bad ones that were in the past. People don't watch them anymore, right? Only the good ones. And so too with science, you have these fashions and things going on, but the only thing that you end up learning 20, 30, 40, 50 years later are the things that actually succeed in explaining things. But there are fashions, just as there are fashions in everything, there are fashions in science. Okay, but still, all these are facts. Whether they explain transition to turbulence is another matter, but they're facts. And so here are all the facts, all put together, everything. Just as I put, you recall we were looking at this, the unfolding that took all the bifurcations and put them all together into one diagram, and the unfolding of the pitchfork. So too now I'm going to put everything together in all linear systems in 2 dimensions in a single picture. So what are the different kind of systems you can have? Node, this famous node word that we're talking about, this is in saddle node behavior. You can, in 2 dimensions, you can have a stable or unstable node, And that is a case in which both eigenvalues are negative or both are positive. And so they act like, as we were saying, that they have exponential growth. And I'm able to represent both in this picture because I didn't put any arrows. If the lambda is negative, if lambda 1 and lambda 2 are negative, then the arrows are going inwards. And if lambda 1 and lambda 2 are positive, then they're going outwards. Okay? And you'll notice that's different from what I called here a star node, where there's only a single lambda, where you can see why it's called a star. They all go out or in. But this one, you see that it's curved. That's to say, asymptotically, that if one of them is bigger than the other, then say it's coming in. Say, then the lambda 2 direction here is smashed down. If lambda 2 is bigger and it's negative, it's smashed down, and now you're going to crawl along the lambda 1 direction at the end. Right? So here these curves are tangent to the x1 axis. When here I deliberately defined lambda 2 to be bigger than lambda 1. Or okay? And the same thing, if there were growth, it would grow in x2 fast. And then it would, no, excuse me, wrong. It would grow in x1. Did I do this right? Ooh, I'm not sure about that ordering. But anyway, they don't go out in at the same speed in all the different directions. That is a star node where you have only a single magnitude. Okay. Then there's a degenerate node, and the degenerate node is what we just saw, this Jordan block thing, where the behavior is exponential or a combination of exponential and linear product. And then the evolution looks like that. Notice here you have this transient growth. You're increasing in this direction and then going out there, if the lambda is positive. Okay? And that's what's shown here, this increasing in x1 like that. Then you could have again, these are all, this covers only the case where lambda 1 and lambda 2 are different and are non-zero. Here, we have them being the same, but non-zero. And here we have them, one of them being, they're different, but one of them is 0 and one of them is not. And that, when it's 0, what does that mean? The system is saying, I don't care. I'm not growing, I'm not decreasing, I don't care. Wherever I am is okay with me. And that's what you see here. You have one direction, this 2 direction, in which it definitely wants to, say, collapse, if lambda 2 is negative. But in the other direction, well, it just stays at whatever x1 value it was. If it was here, it just stays. If it was here, it stays. Okay? And so those are called non-isolated fixed points because you have a whole line of fixed points there. Then there's a saddle, and we talked about that before. You have one stable and one unstable direction here. So you have exponential growth and decay, and those trajectories are hyperbolous. You have, say, decrease in x1 and increase in x2. Okay? All of these are real eigenvalues. When you have complex eigenvalues, you will have either spiral or center behavior. The spiral, depending on the sign of mu, you will be either spiraling in or spiraling out. And I've used the same picture to represent both by not putting in arrows. For a center, mu is 0, and there, that means I don't care. I don't care about my radius. Whatever radius I'm at, I'll just stay. Okay? An eigenvalue 0 always, sometimes it's called marginal because it's between stable and unstable, but it basically means I don't care. Okay? And this says I'm just going round and round. So these are all the possible 2D behaviors, linear behaviors. And just as I said, in 1D, you could understand almost everything already. With 2D, you're pretty much finished. And it's the same thing as in polynomials. This is something that never ceased to amaze me. Of course, you have linear equations, and you have the real numbers, and you get all the solutions to linear equations with real numbers, right? And then when you're around, let's say, 14, maybe, you learn quadratic equations. And probably you're told then, when you're 14, that some systems don't have equations. right? But then when you're maybe 16 or maybe 17, they tell you there's complex numbers and this I, and those things that they told you didn't have equations, well, now you're big enough to handle the fact that they do have equations, but they're called complex and imaginary, right? Am I right about the ages or so? Something like that, right? So you'd think when you get to cubic equations, well, you have to have something new, like J, right? In fourth order, you need some new guy, like K. But no, I suffices. You go to quadratic equations, you have I, and then all solutions of polynomials of any order can be put in those terms. You only need the I. You might think that with each order of equation, you went from linear to quadratic, you needed I. To cubic, you might think you'd need some other thing, but no. And so too, once you have 2D, you really generally don't need anything else. Maybe a little bit, but that's why these little systems, I mean, it's not just an example, just simplification. Pretty much you can take all of fluid dynamics and mechanics and astrophysics and everything, I mean, as far as dynamical systems behavior goes, and reduce it down to just these little things, these little examples. Strictly, it's not just, oh, let's think about it this way. You can't do it computationally, you know, it's big equation there, but in your head, they really do act like this. And if you could project, if you could do computations in zillion variables, you could project it down to things that behave just like this. They would have spiral behavior, or they would have Jordan block behavior. They really would. That's pretty much all there is. Okay. Oh, and then this is a chart that organizes everything. When you take a matrix, then let's think about it. We could look at the eigenvalues are can be put this way in terms of the trace and the determinant. And so here's trace and determinant, and based on the trace and determinant of the matrix, you have all these possibilities that we just wrote about. You have the centers that have zero trace. The trace is just the sum of the diagonals, and then you have unstable, spiral, stable. You know, everything can be located on this picture. Okay, so that's all 2D, behavior, linear behavior. Okay, so linear behavior. Now let's go to nonlinear behavior. That is to say, all this is the analog of what we did in 1D, where we said this. We have f prime positive, unstable, f prime negative, stable. Remember we said this, and that was the classification of all fixed points in 1D. In 2D, we just finished all that classification, but what I'm telling you is we don't have to do a whole new thing for 3D. This is really what pretty much all there is. 3D will probably be mostly like this, or obscure, or hardly ever occur, or something. We're really finished. But not nonlinearly. You recall that after we did this, we said, oh, but this is kind of boring. What about changes in numbers of solutions? What about nonlinearity? And that's when we went on to things like saddle node bifurcations and pitchfork bifurcations, and then eventually transcritical bifurcations. What are the analogs in higher dimensions? And mostly there aren't, I mean, there are other things, but still, mostly, you just have to learn one thing, which is called the Hopf bifurcation. And what is a Hopf bifurcation? It's what happens before and after. Now we're in 2D, so we can't just show it with a line. We have to show it in two space. We have x, y. And it's a transition from a stable spiral to an unstable spiral surrounded by a stable periodic orbit or limit cycle, which mean the same thing. Okay? And now if we wanted to show it the way we learned to show before with a bifurcation diagram, I didn't use those words, but I should have, where we show mu here and we show the stable states along this axis, now we would need 2 dimensions. We would need x and y to show these stable steady states, because the steady states are no longer necessarily points, they are also limit cycles. So what you have here is a transition from a stable spiral where you would be spiraling into here to a limit cycle where here I'm drawing in perspective as best as I can, where this is a cut through a circle like this. And that's what the solution is. Okay? This is the supercritical version. Meaning you go from a situation where you have a single stable to an unstable surrounded by a stable. there is a subcritical version. The subcritical, it's just like with the pitchfork. You go from, let's say if we do it this way, you'd go from an unstable spiral to a stable surrounded by an unstable, just as was the case in the subcritical. And the way we draw it, except that way I did it this way, in this direction with mu. If we drew it in this direction, we would have an unstable surrounding a limit cycle, surrounding a stable fixed point, and then the transition would be to an unstable spiral. And again, keep in mind this very important principle. If you took off your glasses and you went way to the back of the room, this picture looks like this picture. This thing, from mu sufficiently small, it shrinks down to nothing, and what you have is spiraling out. Just like here. You cannot change all the arrows all at once of something. Far enough away, the arrows have to be the same. These are local changes. And so too, this thing here can be shrunk down to this point here, in which case you have this. Okay? So, again, the pictures really say it all, but if you wanted to do a little bit of math, this is, or I shouldn't say math, I should say calculation, because math, of course, encompasses geometry, not merely calculation. This is what you do. This is the normal form for the Hopf bifurcation. This is written in complex form, but that is just a shorthand for writing two equations. In the Cartesian representation of that, you would have this as the linear part, and you'll recognize that. Mu minus omega, omega mu. You recognize that as the matrix representation of mu plus I omega from before when we talked about exponentiating matrices with complex eigenvalues. Right? This is fundamentally a complex matrix. It has a minus omega and omega as off-diagonal terms. Okay? And then it has a saturating cubic term. What does saturating mean? It means, you know, when you have linear terms, we talked about growth. You have growth, oh, but you're going away to who knows where. The saturating means you have something that stops you. When you get big enough, then this term kicks in and it stops you from growing to infinity. And this term written in excuse me, in real terms is the norm is x squared plus y squared here. Yeah, okay, so that's the Cartesian form. The polar form tells you, is more intuitive. It's going to tell you better what's happening. Let us write z as re to the I theta. Then let us differentiate that in time. Re to the I theta. We have two variables, r and theta. So when we get r dot, and then we have to differentiate the e to the I theta part. It's a product rule, right? So we have r dot e to the I theta, and we also have I times r times theta dot. I theta dot times r, and we have r dot e to the I theta. This one is from differentiating the r part, and this one is from differentiating the e to the I theta part. Everybody agree with that? And then here we have mu plus I omega, r e to the I theta, and this becomes an r cubed, e to the I theta. And now when we separate, we divide through by e to the I theta. If we just looked at the real and the imaginary parts of this, we would get the same as this. But what we're going to do at this point is divide through by e to the I theta, which appears in every term, and then look at the real and the imaginary parts, and you get for the r equation, r dot equals mu r minus alpha r, r cubed, and theta dot equals omega minus alpha I, r squared. What does this r dot, what does this r equation remind you of? What is that? You learned very few things so far, and this is one of them. What's this equation for? Pitchfork, exactly. So you have a pitchfork in the r direction. But this equation tells you you're turning. You're doing pitchfork, but all the while you're turning, 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 turning. This one says your frequency doesn't stay constant. It actually changes as you go out in r. But that's a smaller effect. This is the subcritical form. It's going to be just like the one for the pitchfork. Instead of having a minus term here, you're going to have a plus term here. So that's pretty much all that there's to say about the Hopf bifurcation. It's one of the I think it's the other remaining local bifurcation. So you're finished with all the local bifurcations. And then we talk about other way, this top bifurcation creates limit cycles. Limit cycle I use anyway, I don't know if it's a synonym for periodic orbit. Would you say that the same thing? Okay. And I mentioned this word local bifurcation. Local means you can study it by looking at eigenvalues of a fixed point or eigenvalues of something. There's another kind of bifurcation called global, and this is that create limit cycles or destroy limit cycles. There are only a few of them, and that's what this next couple slides tells you about. So this is again origin of limit cycles. Here there are 3 ways you can do it. A very small number of things to learn. This thing here tells you about a saddle node of periodic orbits. Saddle node of periodic orbits. Well, remember what a saddle node was. It was the collision of a stable and unstable pair of things. Supposing your stable and unstable pair of things are limit cycles. So here is a stable limit cycle and an unstable one. And you see that everything is okay topologically. If you're sufficiently high radius, you're coming in. If you're sufficiently low radius, you're coming in. There's a little layer in which you're going out. But everything's okay. You don't have, between this and this, you don't have some big changes of arrows at infinity going, again, same principles before. If you can reduce this to nothing and get this, and it can disappear. Okay? So this is a way in which you can create 2 limit cycles from nothing. Here. You would have a slow area here. I didn't draw it, but there would have some region where this spiraling in is slow. And here it actually would be, it would not merely be slow, as in kind of 0. It would actually change sign so that there would be a place where you'd be going out, and then you'd come back in again. And it could be, this could all happen around an unstable spiral as well. And here are equations, I'm not sure if you call these the normal forms, that will do this behavior. This is this slow area near RC. Okay, so this is another way in which you can make limit cycles. Here is yet another way in which you can make limit cycles. Supposing you had, let's go this way. Supposing you had things arranged in such a way that you had an unstable point and a stable point. And okay, it's natural that you should, when you leave the unstable point, you go to the stable point, right? But supposing things are arranged in such a way that you go to the stable point here, and here you also go to the stable point, but in a different route, like this. You're arranged this way. Now imagine that this little region here collapses. The stable and unstable point approach one another in a saddle node bifurcation. This is an ordinary saddle node bifurcation. They disappear. But because of the way that they were arranged before, this ends up being a limit cycle. And here are equations that do this. This is an equation where you have r equals 0 as one of the fixed points, and the other one is r is 1. So that's 0 and 1. And as for the theta equation here for mu, excuse me, for mu negative, you see that you have 2 fixed points, one stable and one unstable, and that's what's being shown here. One stable and unstable here near pi. Unstable and stable. And here they're going to, this, as you increase mu, this function here, this cosine, shifted cosine, is going to rise until you no longer have, at this point it's marginal, they're fusing, and now you no longer have fixed points. What you have here is a slow region, because again, everything has to be continuous. I keep saying this. Meaning that you don't whisk around like this here. What you do when you're here is you go and, oh, I used to be kind of stable here. Oh, and I used to be kind of stable here. And oh, I used to be kind of stable here. You have a, and those are the, I think there's one more thing I need to show you, and then I'll show you the experimental signatures. Yeah, let me not show you that one quite yet. So what you would see, if you were doing an experiment, even in chemistry, where you might not have your equations already, if you were looking at some time trace, the kind of oscillation you would see would not be like this. It would be like this. This would be your slow place, where you hardly move. This would be where you used to have your stable, steady fixed point, and then you go fast. And that's the kind of time series you would see. If you saw a time series like this, you would say, this looks suspicious. I think it's one of those kind of bifurcations that I saw. And in fact, it has characteristics. We'll look at them in just a second. One of them is one of the homework problems. You can look quantitatively. If you change your control parameter, your temperature difference, your concentration of reactive species, whatever it is that you're using to change your experiment, this length between the two peaks should diverge to infinity as 1 over square root of mu, where mu is the distance from where this limit cycle is formed. Okay. You should be able to plot this period against mu and see what it is. And these are the different kind of signatures that you would see. If you had a Hopf bifurcation, okay, so let's look at all of these signals. Okay, the Hopf bifurcation, its speed is uniform. What's happening here to it is in the radius. It's in the, where are my equations? Yeah, the bifurcation is happening in the radius here. You have a pitchfork bifurcation in R. The speed is pretty much staying uniform. Not entirely, but to the highest or lowest order, it's staying uniform. What's changing is the R. Okay? And that is what we're showing here. If you looked at your experimental or computational limit cycle, what you would see is that the amplitude, the R, is changing. And it changes like the square root of R because, as we saw, yes, the solutions to this are R equals 0 and R squared equals mu over alpha. So it grows, so R goes like square root of mu over alpha. The amplitude grows. You see that it grows from 0. That's when I told you to squint your eyes and see this as tiny, 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 tiny. Okay, it grows like square root of mu, this thing here. And that, so if you see a signal in your experiment or your computation, and you change your mu, and the period doesn't change very much, but your amplitude does, then that is probably due to supercritical Hopf bifurcation. You can see your data and you say, oh, I think maybe I have supercritical Hopf bifurcation. The saddle node of limit cycles, we saw there that the action was in R, and the period, okay, here, what do we see here?